right, so indicators were the next slide on the PowerPoint notes. What is an indicator? What do you think it does? Indicates what?
pH.
So like you raising your hand indicates to me you have a question, right? You give me confused look indicates to me you're like confused. But an indicator for this specific one is going to indicate what? The pH, right? It's going to tell us either a number, like it'll indicate the color of a solution, which we associate with a number, pH 0 to 14, or it might just say, hey, I'm in the acid realm, hey, I'm in the base realm. It doesn't actually give us a quantity, like it just tells us the general region. So phenolphthalein is an indicator, and what two colors are associated with phenolphthalein? Okay, so one is clear and one is pink. All right, so clear is associated with acidic or basic in terms of solutions for phenolphthalein. Acidic, and pink is basic. So again, that doesn't really tell us the pH, but we know it's above or below 7. So you have to know how phenolphthalein changes colors upon different pHs or different solutions. The other common pH indicator that we use is litmus paper. Litmus paper has two initial colors. What are they? Blue and red. Blue and red. Okay, so they're initially, it's like a piece of paper and it's blue, and there's a piece of paper and it's red. If I take the blue paper and I dip it into a base, what color does it turn? It stays blue. So if I put blue paper in base, it's going to stay blue. If I put blue paper in acid, it's going to change red. Okay, so we're going to kind of use that same logic. Blue paper in base. Let me kind of make my format here. That's going to be blue. Okay, if I have red paper and I put it in acid, what color does it turn? Red. Stays red. Okay, so it's going to stay red. And if I put red paper in base, what color should it change? Blue. So basically, if it turns blue, or if it is a base, it'll either change the paper blue or it'll stay blue. If the solution is acidic, it's either going to change the paper red or it's going to stay red, depending on kind of what paper we are starting with. Okay, so those are two very common indicators we should know a lot about. We'll talk about how to determine the pH of a weak acid later. Let's skip that one for now. All right, down here, I'm going to go down to this data table first. Decide which substance is an acid. Talk in your groups. Take like 30 seconds. Talk in your groups. So W, X, Y, or Z, which is the acid? Z. Why are we saying Z? Okay, so that's like one of really obvious traits, right? It's the only one that tastes sour. What if it did taste bitter? What would we associate that with? Base. Okay, so it's definitely not the case. What would an acid feel like? Would it feel slippery? What would it? If you had like an open cut, yes, it would burn. But what would it just feel like in general? Just liquid, just watery. But bases feel slippery. That's like soap. Think of soap for bases. Litmus paper. What should the acid solution turn the blue litmus paper? It should turn it red, right? And that's what it does here. It turns litmus red. It didn't tell us what it turns. It didn't tell us any information about the blue one because it didn't turn. Okay, so yeah, definitely Z is the acid. All right, hydroxide concentrations are here, which would be acidic. And those are exponents, by the way. I know it doesn't look like it.
So it's 10 to the 4th.
Yep, 10 to the negative 4th, 10 to the negative 6th, and so forth. Take 30 seconds. Yeah. Why would you say D?
Because it'll have a hydronium concentration of 10 to the power of -6.
So how can you do that logic in your head so quickly? What are you looking at?
The -8 and the -14.
Okay, so hydronium, if hydroxide is 1 times 10 to the -8, remember together when you multiply hydronium times hydroxide, they have to equal what? 1 times 10 to the negative 14th. So you add your exponent, so that should be 1 times 10 to the negative 6. Which of these values is bigger? Negative 6 is bigger by how many?
2 zeros.
2 zeros, so you're basically saying it's 100-fold greater. It's 100 times greater.
Well, I'm thinking the opposite.
Well, that's why it's very important for us to understand hydroxide is always just like a high quantity of hydroxide is associated with bases, a high quantity of hydronium is associated with acids. Okay, so we have to identify that first, and then we have to compare the numbers. I know it's scientific notation, but you guys are well past this in math. Like, you can do this. Negative 8 is smaller than negative 6, so this is a smaller quantity of base and a larger quantity of the acidic ion. Therefore, this should be the acidic one. What's the hydronium in this solution? Okay, somebody other than the Corbin, next one. So if this is negative 2, that's going to be, is that a high or a low amount of hydroxide
Low.
compared to all of these other ones?
Oh, my.
0.01, right? This is 0.0001, this is 0.0001, this is 1. Right, so that's much, much, much higher than the rest of these. So that's a high quantity for hydroxide, so that's going to be pretty what? Pretty basic, okay? So not carbon this time. What is the hydronium for B? 10 to the negative 10th, right? So hydroxide's 10 to the negative 4, hydronium's 10 to the negative 10. Who's larger? Negative 4, so hydroxide by like a million times, right? 6 zeros difference. That's a lot more hydroxide. This is definitely going to be basic. This is 10 to the negative 6. What's hydronium? 10 to the negative 8. So who's bigger? Hydroxide again. So yet again, it's basic. So we had 3 right in a row that were basic, basic, basic. This one had a what's the break point basically? What's the middle? Negative 7, right? If they were negative 7 and negative 7, they would be pH what? pH 7, which would be neutral, which would be neither acidic nor basic. But now, since we broke that barrier, we went to the negative 8th side of things. That's when we start to say, okay, well, we got less base, we actually have more acid now, we flip-flop. So now we've made our solution acidic. This should be a quick mental thought process. You should not have to calculate on anything that's just 1 times 10 to the negative 8. The exponent tells a story, okay? So what you should also be able to do is actually tell the pH of each of these. And I'm telling you this now because when you have a quiz and it's a quick quiz and you're trying to calculate everything, you just won't have time. It's more about understanding the logic of like these numbers. So if I have substance A through D here, and I want you to tell me the pH of each of these, it should take you 30 seconds to pretty much tell me them all. Okay, so I'll demonstrate for the first one. If I have an OH concentration of 10 to the negative 2, what's the POH for that? 2. It's 2 because negative log of hydroxide concentration, right? So you'd be doing this is 1 time or is negative log of 1 times 10 to the negative 2. Well, log base 10, this base 10 and this base 10 basically cancel each other out. So log of whatever this is just what the exponent is. So therefore, it's just what the exponent is. It's 2. So if the POH is 2, what's the pH? 12, okay? Next one is this. What's this POH for B? 4, what's the pH? 10, okay? So we're getting more or less basic. Less. Next one, POH is 6, pH is 8, still basic, right? And then next, POH 8, and then pH 6. So we finally made it to the acidic realm when we say pH of 6, because we're down below 7. So just don't forget that. Since they gave us hydroxide, that's where we had to go to POH first, and then jump to pH. You okay? All right. So those, like I said, those just should be pretty fast. Okay. Tell me these again. This is that slide you guys had your notes on. Phenolphthalein should be what in base? Bright pink. It's like a magenta pink. Look at this right here. Really, really pink. And then it should be clear in acidic or neutral, actually. So just understand that it is neutral. And then I like to see if I can come up with my little, this is my Valley girl, California girl, Silicon Valley kind of thing. All right, guys, litmus paper is going to go from blue to red. That's indicating blue to red acid. And then red to blue base. Okay, so you should know blue to red acid. It kind of rhymes. And then red to blue base. Okay, so if it's blue, it's definitely trying to indicate to you a pH of above 7. All right, so those are the 2 most common indicators. And you saw my joke. I thought it was funny. Haha, basic humor. Ha. Thank you. Okay. So, and this really is just a fun fact. Who's ever seen like the hydrangea flowers? Okay, what colors have you seen? Well, like what? Pinks, blues, maybe some yellows in their like primary phases of developing, maybe like a purple. So if you've never seen them, you might notice them now, but their pH of the soil changes their colors. They have a natural indicator in the flower. So if the pH of the soil is kind of below 7, so it's acidic, what do you think the color of the flower would be? It's very much like litmus. It would be reddish pinkish. So like this one here is kind of pinkish red, that would be acidic soil. So then what color do you think would be exhibited in a basic pH? Bluish. And then like a neutral? Purplish. So you actually can change the colors of your flowers by adding vinegar to the soil to modify the pH. So kind of neat. These are a slew of indicators. We can opt to use any indicator for a specific experiment. Those experiments are called titrations. We're going to talk about that in like 10 minutes. But you choose an indicator based on what when you think the equivalence point is going to be achieved. So we have a lot to choose from to like really personalize our experiments. But then here's your phenolphthalein again. Phenolphthalein changes at what? When does it change? About pH what?
7.
No.
7. Wait. Oh, 9.
Yeah, so it's changing in basic pH because it's going to actually be clear all the way from 0 to about 8.5-ish, and then it's going to start to change right past that. So that's something very specific we look for in the experiment. And then there's a lot of natural indicators. If you've ever seen colors change, like with your fruits and vegetables, it's because their acidity or acidity is changing. One that I've experienced myself is cabbage juice, red cabbage. It changes from red to like a pink to like a purple to a blue to a green to a yellowish over the course from 0 to 14 pH. You could actually do this. You could do this at home. You could see a lot of color changes based on the pigments found in these fruits and vegetables. So it's kind of neat. Okay, check this real fast. This is on your problem set. I just want you to see the true-false stuff because you guys were telling me you're okay with a lot of the calculations, especially because you can check yourself, but the conceptual side of things you want to double check. So write down the right answer where you need to if you have like a mistake. Give me a thumbs up when you're good. All right, any questions right now on those? Which ones do we have a mistake on?
3, 4,
3. Chemists have a special system for naming bases. This is not true only because like in our acids we have to go, oh, is it binary? We say hydro. If it's ternary, we don't say hydro. And we change the ic and the ate and the os. So, huh?
What do we sometimes do? Sometimes we do.
No, so for acids, this is number 3. Chemists have a special system for naming bases. That is not true because our system isn't special. It's just whatever the chemistry is. Sodium hydroxide. It's just the ion names. There's no special changing of that naming system. But acids, we change the naming system to modify it to be a different way of naming. What else do you say? 4? In an acidic solution that is greater than hydroxide. Hydronium is the acidic ion, so it should always be greater than hydroxide, always, if it's acidic. And then 10, the ammonium ion is a bronzolaric base. So that cannot be true because the ammonium ion cannot be a base because bases accept protons and it already has an extra H plus and it cannot take on any more. Its most common version of itself is ammonia, this right here. This is the base because as you can see itself has just 3 H's, but upon accepting another H it has now H4 and a plus. So it's already done its job of accepting bases, or H pluses, so it can't do it again. So that's why that specific one is not true. Any others right now? Speak now. We rolling, okay. We're going to write down some examples of reactions. So either on your paper that I've provided for you, I think. Nope, I did not give you those examples. They're all going to be here. So what were the two types of acid-base example reactions you guys wrote down? They're called two different things. You took your notes on those slides. Say again? Neutralization and hydrolysis. So they're very quirky in their names. Neutralization, hydrolysis. You think we're talking about totally different reactions, but we're not. Look at this reaction. HX plus YOH, this is just a generic form, of course, makes YX and HOH. What kind of reaction of our 5 types of reactions is this? Double replacement, right? So is it new? It's literally just trade your partners, crisscross charges. Trade your partners, crisscross charges, balance. That's it. So it's not a new reaction. It's just we're terming it special because it's in acids and bases, and so we're only really using things that are acidic or basic in nature. So we're going to do an example of this. But remember, anytime you have an acid and a base, generally when they add together to do double replacement, they should make salts and waters. Salts are just anything ionic. And of course, water is water. We won't always make water because it does depend on what acids and bases we start with, but that's a good example that we'll usually see. So I want you guys to write down these 4 reactions. Let's start with the first one together. Okay, so this is quick because you should know your formulas, specifically your polys as needed. What is hydrochloric acid, everybody? HCl. What is sodium hydroxide? NaOH, right? And to help you, I'm going to write down the charges underneath here so you understand cations pair with anions, cations pair with anions. So this is our H with a plus charge. This is chlorine with a negative charge. This is sodium with a plus charge. This is hydroxide, happy family hydroxide, meaning do not break OH up. It is a happy family with a negative. Okay? So in our double replacement, this plus has to get with what? Right, the other minus, which you're saying is OH, right? So what do we make? We make HOH, and those are all plus 1s and minus 1s, so our crisscrossing charges are really easy here because they're all 1s. And then other one, good. No one's putting ClNA that looks ugly, it's wrong. We now can see the ugliness of our chemical formulas because if we've never seen it before, you're like, maybe I'm not in the right place here. So this plus gets with that negative. So plus NaCl. And is it balanced? Yeah, we're good. Okay, we gotta do the next 3. And you can just write down the formulas. You don't have to write down the names unless you want to practice that, because it is important to practice. I see some carbonates and bicarbonates. You're confused. Let me address that real fast. What's hydrochloric acid? HCl. What do we have for sodium bicarbonate so far? Not C, so yes, H. So when you see bi, it actually means add an H plus. So carbonate is what? CO3 2 minus. When you have bi in the front, you're adding an H plus. So when you merge those together, what do you get as your entire ion? 2. No, we're not going to crisscross charges. This is going to be an ion still. So we just want to merge them and combine their charges. HCO3 with a 1 minus charge. Because that 2 negative and that 1 plus add up together to be negative 1. And that being a negative 1 and that being a plus 1 overall gives us that. All right, you guys should be good from there. saw a couple of us put HCO3. Do you think we could simplify that? H2CO3. So instead of putting HCO3, we're just pulling the H's together as 2. That's it. We just write these on your notes on Tuesday. Current notes from Tuesday. Give them out. Alright, so I do expect you to have some background knowledge here. Help me out here. Give me a table. Give me the first part, the reactants here.
HNO3.
HNO3. I'm going to put parentheses around nitrate so we can tell it's a happy family plus what?
MgOH.
Mg parentheses OH parentheses 2. Good. Current table, pick up. Do your double replacement. Let's go. Magnesium nitrate, MgNO3 like this. We got to crisscross charges. Remember, every single time you get to crisscross charges, because it's ions, 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 ions all the way through. What was magnesium's charge over here? 2. What's nitrate's charge over here? 1. There's a 1. That's not the charge. That's a subscript of a 3. So there's a 1 charge. So then what's this? Mg. Good. And what else, guys?
Water.
HOH. Okay, you can write it as H2O. I think it's really easy to write as HOH because you can see how the balancing works out a little bit better. So I see I have 2 nitrates here, right guys? So what do I need on that side? 2 in the front, and that makes 2 H's. And there's 2 hydroxides, so what do I need here? Okay, 2 in front of water. Alright, Ariel's table, you guys start with the last one, reactants-wise. Let's go, somebody do your table. Because calcium is a 2 charge, you guys have a periodic table probably nearby if you can't see that one, okay? So the calcium is a 2 charge, hydroxide is 1. Keep going, what's acetic acid? Okay, and I'm going to put parentheses around that so it's very obvious that it's its own poly. Chandler's table? Good. And then balance that, guys. Okay. One more thing.
I guess it's 2 in front of them. Oh, wait.
Yeah, there's 2 acetates here. We need 2 acetates here, so we're going to put a 2 in the front of acetic acid. Good. All right, so now we do so this was called neutralization because, as you can imagine, acids are really acidic, bases are really basic. When you put them together, they should generally be close to what? pH 7, neutral, right? Hence neutralization reaction. Anytime you have an acid and a base reacting, we call it neutralization. Anytime you have the opposite, 100%, 180 degrees opposite, is where we actually have the salt that was previously produced by the acid and base coming together, and we simply take the salt, meaning the ionic compound, and we put it in water. Again, the same thing's going to happen. The positive, negative, negative are going to do the double replacement process. The cation of the salt gets with the hydroxide. to reform this base, and the acidic portion of the water, so the H plus of water, gets with the anion of the salt to reform the acid. So yet again, it's just double replacement. There's no secret. We just flip-flop places, crisscross charges, balance, same thing. So the only thing we have to compare though at the end, which makes it a little bit different, is the NPH going to be acidic, basic, or neutral? And so that's the big question. So let's think about this. How many strong acids did we memorize? 6. How many strong bases did we memorize? 8. So this is the B on the periodic table. So if I have an acid that's strong and a base that's strong, and I end up making a strong acid and a strong base, what do you guys think the pH is going to be of the solution at the end? Why neutral? Right, it's a balance between the strong acid and strong base. So if I change that to be a weak acid that was also produced with a strong base, what do you think the pH of the solution is going to be at the end? Why? Right, you have more hydroxide ions being formed from the strong base. You don't have very many hydronium ions being formed from the weak acid. It's definitely going to have more hydroxide in the end. It's going to be very basic. All right, and then what's the last scenario? Strong acid and weak base, and that would yield a what type of solution? Acidic. So we basically can classify the type of solution based on the comparison of strongs and strongs, weaks and weaks, and so forth. But what does that mean? You have to know. You got to know your strong stuff. You got to know all your strong acids and all your strong bases so that you can quickly look at that and go, yeah, it's going to be acidic or it's going to be basic. And then last call on this slide, hydrolysis. You actually know how to break down terms. You've got it like in biology with photolysis or photosynthesis, things like that. If you ever see lysis, it means to break. And in this case, who's doing that breaking? Water. So it says hydro, which to us means a lot of things now because we have so much in our brain, but it is referring to water. So water's breaking stuff up. Well, what is it breaking up? The salt, and then it reforms the acid and base it previously was formed from. Okay, so these equations look a little different because it just says hydrolysis of blank. So that means you have to know to add what? Water. So when it says hydrolysis of blank, we have to say, okay, well, what's sodium chloride? NaCl, and we're going to add what? Good. I don't like to write H2O. I like to write HOH because it helps me see the ions better. It's just a technique that's going to be used. Everybody's writing this down with me right now. Let's go. So who does sodium go with? Good. OH. It's going to get with the anion. So it makes who? NaOH. And then the other one is good. H plus is going to get with Cl minus. Crisscrossing charges gives us HCl. Okay? You guys do the rest. So just do the double replacement and balance those so we can talk about those 4 reactions in a moment. Crisscross charges, people. Look at your polys if you need them. Don't forget to crisscross both charges though. So one has a charge, the other one has a charge, and you're crisscrossing both. There's an ion. 18. Yeah, he was over. Okay, he just wasn't on my list. All right, Chandler, so we'll get me started on this one. Calcium phosphate is hydrolyzed. Good. So we just cross both charges. Calcium is a 2, phosphate is a 3. Good. Hydrolysis means what? HOH. Keep going. Did you say PA first?
I said yield.
Oh, yield. Okay.
H3PO.
Good. H3PO4. So pause there for a second. So he did the phosphate ion with the H plus ion. This is H plus. This is phosphate. PO4 3 minus. He crisscross charges. Thank you. And CaOH 2, and that's the Ca plus 2 plus, and hydroxide OH minus. So we are crisscrossing charges like a champ because we don't want to screw that up. Balance it, guys. Oh,
That's what I
balance.
said.
Always.
So there's, you're gonna put a 2 in front of the H3,
Okay, because there's 2 phosphates and you want 2 phosphates, okay?
and then a 3 in front of the H3.
In front of, let's do HOH at the end, just because, just trust me.
Okay. I don't know what else.
Well,
Okay.
how many calciums are on the reactor?
Yeah, 3. Oh, we need to put 3 in front of it.
Okay, so now we have 3 calciums and the 2 phosphates, okay? Now, look how many hydroxides I have. How many's a lot? 6. 3 times 2 is 6. So what do I need here? A 6, because that's going to give me 6 hydroxides. And then how many H's does that give me? 6. And guess how many H's I had? 6. Okay. Okay, you guys are next. Lithium nitrate.
LiO3
Okay.
plus HOH.
All right, somebody else pick up. Let's go. Yeah, so lithium hydroxide, so that's our Li was our cation, hydroxide was our anion. We brought them together. And what else? Somebody else?
HNO3.
H, good, NO3, and that was because H plus was our cation, nitro was our anion, and everything here had a 1, 1, 1, 1 charge. That was balanced, yeah. Okay, and then let's go back and forth. You guys get me started on aluminum bromide.
AlBr3
AlBr3, good, because aluminum has a 3 plus charge, bromine has a 1 minus. You crisscross very nicely.
plus HOH.
All right, Chandler, so you'll pick up. Hold up. Oh, Al, good.
Yeah.
Because Al has a 3 plus charge, hydroxide has a 1 minus charge. Crisscross.
Yeah.
And
And then HBr.
HBr, and those are both 1 and 1, 1 plus 1 minus.
Yeah.
Everybody balance, what do I need?
A 3.
And I think one more thing, right?
3 to HBr.
Good. Good. Okay. All right, so now let's look at the resulting solutions we just formed, which are all the products. And I want you to write above or below the products, SA for strong acid, SB for strong base, WA for weak acid, WB for weak base. Okay, so I'll demonstrate the first one for you. Is this hydroxide a strong or weak base? Strong. It's on your list of 8 strongs, which is up in your head at this point. So this is a strong base for me. This is an acid because it has an H in the front. Is it a strong or weak acid? Strong. It's one of your memorized list of 6 strong acids. Okay, so I have a strong combo. What does that equate to in terms of pH? Neutral. So we're going to write neutral out here to the side. All right. You might want to look at your list for now because I'm sure you're still memorizing, but you need to write down those abbreviations on all the rest of them. Don't guess. Look at your list. Look at your list. You write them down on your notes. Tuesday, Monday. Have your stuff in front of you. get a list. All right, come back to me, everybody. What am I labeling on phosphoric acid? Lab crowd, come on. Weak acid, and this is a no. Where's a okay? So I'm gonna point at this PR table just because it's what I'm working with. So it starts at lithium. The B starts at lithium, goes down to sodium, potassium, rubidium, cesium, and then goes over to barium, strontium, calcium. So that 1, 2, 3, 4, 5, 6, 7, 8. Those are the 8 strong bases. Okay, so this is what? Strong base, so this yields an overall what solution? Say again? Basic solution. Okay, this is what? Strong base, good. And this is a strong acid, so we have a what? Neutral solution. And the last one? Weak base and strong acid, so we should have a, oh, sorry, I didn't mean to put B there. Good, acidic solution. All right, so what should litmus paper turn in this solution? What should, okay, so either one red or blue paper should stay what? Should go red. This solution, it might go purplish, but it actually will, the red will stay red, the blue will stay blue, which to us says neither means neutral. And then this one should go what color? Blue. Good. All right, stretch break. Stretch break. We have here, I'm making you stretch. Come get these. Go to the bathroom. You got like a minute. We're gonna do these. Okay. Grab that. We're gonna talk about titrations, and that's our last topic for now. Take the monkey. Give me a monkey. So specifically, you need to review, maybe look back over your notes for a moment. You can finish your crossword. Let's take a minute. Try finishing that crossword. So you have your stuff from.
I got one left or something.
Ask a friend.
Do you have
This is stuff I have.
Tuesday. So we did notes here. We did some of these on notes, which you can watch and specifically. That was the PS.
Oh, actually, you guys, instead, if you want to look at PS 19B, it's right next to PS 19A. We're going to start that at the end of class, but you can actually go ahead and do a couple of those reactions. So how about if you break for a minute, you guys start reactions, which I think is starting at question 1, part 1. So instead, let's go here. So PS 19B, let's take a couple minutes and work through that. You can't do everything yet, though. Are you back with me? Scoot your problem set to the side for me, and then we're going to do titration stuff. And this is the paper I just handed out, the lecture sheet, that's got nothing on the back. It's got a little L on it for like a graph. Got it? Okay. So, write down, and you guys will see this on your paper too, the word titration. Because I want you to know that term means a chemical, like, experimental process. So, it's actually a volumetric analysis procedure. So, think it's a lab. It's literally us doing a lab, but we're going to do the lab kind of on paper first. I have some images to show you what's going on. We'll do an online version of it so you get the hang of it, so you understand like the extreme accuracy that's required to make it work. And then Monday we actually will do the titration. Okay, so it's a volumetric analysis procedure. So what we do is we have to have an acid and base reaction. So it literally is a process of acid plus base. We use very, very specific quantities like volumes. And to accurately measure, we use this big long thing. It's like a really long piece of glass, or about this tall, called a burette. okay? And that burette is like close to $90 or $100 the whole thing. Like it's pretty expensive because it's supposed to be really accurate. So the burette's the long piece of glass, and then there's this little thing down here that dispenses. You actually twirl it, and when you twirl that little knob, it dispenses like 1 milliliter at a time, and that's called a stopcock. Yep, that's the word we chose for that. Okay, so burette and stopcock, and then we have this down here called a what? What's this piece of glassware? A flask. So that's generally what we use in our setups. And then in the burette, we'll put like a known molarity, and then down here we'll put an unknown molarity. And what we do is we run the procedure, we do the stoichiometry, the math behind it, and we calculate the unknown concentration. We calculate like the molarity of the substance down here. But so we can't tell what's happening because it's all clear, 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 clear. So we actually add an indicator. And what indicator do we add here? Say it for me.
Phenol.
Phenyl.
Phenolphthalein.
Yeah, phenolphthalein. Phenolphthalein. Okay, so we added phenolphthalein. And what we know about this experiment is that it should meet something called the equivalence point. It should meet at about pH 8 or 9. So we opted to choose phenolphthalein because that's when it changes color to what? Pink. Okay. So we titrate. We're titrating. That's what the process is called. Titrating a specific volume, and we're just dispensing volumes down, 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 and down until we hit the pink color. Actually, the light pink colors we're looking for, if we get to the magenta, it's called over titrating because you've gone too far. You have to start your experiment over. Okay, so it's got this fancy glassware. We're going to actually look at the math behind it now. Okay, so before I do the math, what we get, and this is what I want you to graph on your little L graph. Okay, so what we get is this beautiful graph. It's a big long curve, and it tracks pH versus volume. Does yours say pH on it?
No.
Okay, so you're putting pH on the y-axis. You're putting volume of, and I'm using sodium hydroxide, but you can just say volume of base added on the x-axis. And generally that's in milliliters because we use just little volumes at a time, hence volumetric analysis, we're looking at volumes. And as we add base, well, what are we adding it to? That's the thing. In our flask, and that was the picture you saw earlier, we in this case have an acid in our flask. So how is that indicated on the graph? That we're starting with an acid.
Sort of lower on the y-axis.
Right, we're starting at pH below 7. So we're actually starting at pH 1-ish. And so you don't have to plot these points this specifically, but give it a general curve, okay? So why, if I'm starting with an acid pH, when I add this base, what do you observe is happening? Why is it going up? Okay, so we're adding a base, the pH goes up. We're adding a base, the pH goes up. We're adding a base, the pH goes up. Zoom, it actually has a really sharp incline because of how the logs work out. Logs are exponential functions, right? So they have this little zoom nature, or they're related to exponential functions. So it goes up, 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 zooms up, hits a point where we call the equivalence point. So you need to note that term in the middle of the long vertical section. Okay, so it has to be in the middle of the vertical section. Okay, so that's the equivalence point. And what you should recognize from that point is a specific scenario. I'll write that down right here. Equivalence point is where moles of acid equals moles of base. And so that's really important for us to know. That's the definition of the equivalence point. If you're just going to memorize it, but I think you should write that down. Now, we've added base, 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 we've met the equivalence point. This is all in clear solution. We can't tell anything what's happening. So we keep adding more base, and we keep adding more base, and we keep adding more base. And then, what does phenolphthalein start to do? It starts to change color at around pH 8 or 9. So when we see that color change, we're like, whoa, stop the titration, we are done. Okay? Now, what we really want is that color change to happen where the equivalence point is. Did it here?
No.
But it's kind of close. So we're okay with like understanding, okay, we're close enough, let's call it a day. That's going to be when we stop the titration, that's when we stop the experiment. But truly what that point up there is called is not the equivalence point, but this is called the end point. Okay, so you should know the end point is when the indicator changes color. So we really want the equivalence point and the end point to be really close together, but we can't always have that level of accuracy just because our equipment may not let us or the indicators may not let us. But what that's supposed to tell us is end the titration. When you see the color change, stop the titration. But this graph is just because I want you to see the whole graph, I want you to see the whole shebang. If I continued past the indicator's endpoint, I could add base, add base, add base, add base, add base, and it would eventually level out around pH what? 12, 13, maybe 14, but 14 would be really basic. So because we're diluting it within this acid, it may not be up to pH 14 because it would essentially mean there's no acid there. Okay, so again, we started off in the flask with what? An unknown concentration of a what? Of an acid. Okay, so we have our unknown concentration of an acid. We added what to it? A base of known concentration, like maybe it's 1 molar sodium hydroxide. So we added base, what happens to pH? Increases, shoots up, we hit the what point? The equivalence point, which definition is what? Good. Hold on, say again. It is the middle, oh, that helps us identify where the equivalence point is. It's the middle of the vertical section, but the definition is what? Right, so this is important for us to know. But we can't see that, so we use an indicator to help us to tell us when to stop the titration. So the indicator will indicate the what? At what point? It'll indicate by color change the what point? The end point. It'll indicate to us stop the titration, end point. And then, of course, this graph just goes on because I wanted you to see the rest of it. All right, so this is very experimental based, and you can see all the data that goes along with it. Moving on. You have a little graph drawn? Label all the points. Okay, so and what's this piece of equipment called again? Burette. And then we're going to, I think we can do this. Endpoint, equivalence point, we know the definitions of that, so let's keep going. All right, so this is next on your sheet, right? So basically what I've done for you is I've walked through the stoichiometric thought process, but don't write this down because it's not about you memorizing a process, it's about stoichiometry. What's always our purpose every single time, anytime we do stoich? To convert by units, but how do we know like when to move on to the next unit? Okay, so we might use mole ratios, we use unit cancellation the whole time. So if you can do unit cancellation, you can do this the whole time. Literally no different than anything we've ever done. But that's what this whole process is starting with. So I'm going to show you an example first with one of these examples, and then we can come back up here if we need to. Okay, so here's how we process this data. Now at least you'll understand what's happening when you read these scenarios, okay? Because you know what a titration kind of looks like. A student titrates 20 milliliters of a sample of a solution of HBr. The titration requires 20.05 milliliters of a 0.1819 molar sodium hydroxide solution. And then that's to meet the equivalence point. Okay? What is the molarity of the HBr solution? All right, so right now you're like, okay, I kind of know what's going on. I'm adding something to something. I hit the equivalence point. It wants to know the unknown concentration. So before we move on, we always have to identify who's the titrant and who's the analyte. These are fancy words for known and unknown. So who's the known? Who do we know both the molarity and the volume for? Okay, sodium hydroxide. So who's the analyte? Good. So hydrobromic acid. So that's our question. The analyte is who we're analyzing, which makes sense because it kind of sounds like that. And so our question is HBr. Okay, so that's nice. We can identify that very quickly. So we always want to begin the process of stoichiometry with the known. Okay, so who is that here? The known. Who's the known here?
Oh, sodium
hydroxide, because that's the one we know both the volume and the molarity for. Okay, so we want to begin stoich with NaOH. All right, so I will tell you, I missed this, I skipped this first step just because I wanted you to analyze the problem first, but this is a step-by-step process, okay? So we want to write a balanced chemical equation out first. All right, so who are two reactants? hydrobromic acid and, okay, and what kind of reaction is this, guys? Double replacement. Term it in the acid-base world. Neutralization, because it's an acid-base reaction. Every single time it's going to be a neutralization reaction. Who are the products? Write this down with me, okay? HOH and who? And ABR. Okay, so that's our plus and that's our negative. All right, it's balanced, right? Okay, so 1 balanced equation's done. 2, I'm going to write down beneath each of these the known data points. So what do we know about NaOH from the question up here?
It's 20.05 mils.
20.05 mils. So follow what I'm doing here because I promise this will help you a lot on the next sequential examples. And what else do we know about it?
It has a 0.1.
1819 concentration. Right, molar concentration. What do we know about HBr according to the question?
It's 20 milliliters.
20 milliliters of it. And we don't know the concentration. We don't know the molarity. Now it's really easy. You can tell from just the data that you've written, you have to start with this guy, the sodium hydroxide, because you don't know enough about HBr to even get started. And that's our final question, so we must end our process with that. So we have to use this collectively together. And you guys remember what molarity is? Molarity is moles per liter. Okay, so molarity is mole per liter. Notice that my molarity is here, but I have this in milliliters, so what do you think I should probably do that first? Convert that to liters, because I can't really work with milliliters in this standpoint. So what is 20.05 milliliters in liters? Good, you're bouncing the decimal back 1, 2, 3 places because there's 1,000 milliliters in a liter. So 0.02005 liters. All right, we're just doing stoic. I've used this now. What do I need to do with this? Well, remember, I don't want to write M. I want to write moles per liter because that helps me see the units to cancel. So do I want to put this number on top or this number on bottom? On top, because this right here is 0.1819 moles of who? Sodium hydroxide per 1 liter, and that's just of the solution, the sodium hydroxide solution. So I'll just put solution. Are we okay so far? Yeah? Okay, we're checking. We got the volume taken care of. We got the molarity taken care of. The liters of NaOH solution cancels out. Now, we've exhausted sodium hydroxide information. We want to bounce across the bridge from sodium hydroxide to hydrobromic acid. How do I do that? The mole ratio. What's the mole ratio, guys? 1 to 1. So there's a 1 coefficient here and there's a 1 coefficient here. Now I can make that jump. So what do I write here?
1 mole of sodium hydroxide.
So 1 mole of sodium hydroxide goes on bottom because sodium hydroxide has to cancel, right? Moles of sodium hydroxide have to cancel. Up top, 1 mole of HBr, because those are, I'm going to put BCE here, if it helps you remember. Now we're so close, right? Molarity is what we're looking for. Again, what's molarity? Moles over liters, right? So if I have sodium hydroxide moles that cancel, how do I get the units of moles per liter? I already have moles right here. Say again? You would change 20 milliliters to liters, so what's this in liters?
0.02.
1, 2, 3, so 0.02 is liters. So how do I get moles per liter? So I got moles. You have to put liter on bottom. We're just going to basically divide by liters. So you can stop here, hit equals on your calculator, get moles, and just in a separate step, divide by liters to get moles per liter. Or you can literally just multiply by the inverse. Because multiplying by the inverse, is that not the same as dividing? So I'm a fan of not stopping, and I'm going to put a 1 there just to be my placeholder, and my 0.0200 liters in the bottom to show me dividing by liters. And what's that answer? Oh, I don't want to cancel that.
put 0.1823.
0.18235.
Initially.
All right, so let's round that to sig figs. How many sig figs not working with this whole problem, guys?
4.
4 the whole time, right? So can we round that to correct sig figs?
0.182.
Yep, 24. Sounds good. And that's moles per liter of HBr, because both of those units, moles, HBr, liters of the HBr solution, those are the 2 units left. So moles per liter gives us molarity of HBr. I want you to talk in your groups, 30 seconds, the exact process we took. Talk through every single step.
We write a
So you took
BC first.
all you.
Write the BC.
Every step.
Multiply that by your moles. Yeah, the molarity.
All right, you guys are doing this one. And you can talk in your groups, do what you got to do. You have kind of a step-by-step process you should be working with. In your groups specifically, and I know reading sometimes can be a little challenge to pull out the information, so maybe call out the 2 reactants you see. Make sure we're on the same page.
Good in here. No, loading is 1.
You just write the data underneath it, you can hijack it on all that, it just helps you understand.
H parentheses C2H3O2. That's balance.
You want to proceed with 3, and there's 3 sample questions of the rest. We got about 15 minutes. You guys can talk through now. I'm going to try to let everybody finish 2 before I solve the board. So you guys can talk in your groups as needed too. follow the same exact process from question 1. You need to go look back at your work.
Would you want to talk to your make sure it was confused?
You guys talk about.
So, guys,
Which false charges do you
go to the second figure.
It was close.
You're talking about this one.
Yeah, it was close. So you didn't break the whole thing.
I don't know why I was.
Okay, let me know the process. You keep on going. You guys get 0.8 for each 3 molar.
Yeah.
Awesome. Okay, so you're moving on to 3, if you're able to. We'll leave this here for a moment. You can at least get the beginning, like BCs on all of them, minimum. be strontium 2, so you're going to cross discharges. What you guys get for strontium hydroxide concentration? Number 3. 1, 2, 3, 4, 7.
Molar.
Who actually calculated the pH on this one? Most of us just skipped over it. All right, let's chat real fast if you're in the middle and then pause. All right, guys. So the question of pH was pH is for the strontium hydroxide. That's like what we did on Prop Set 19. Okay, so just how do I find the pH from this solution? Tell me your thoughts. Okay, first off, classify. Is this an acid or a base? A base, because it's got what? It's got a hydroxide on it. So from a base, what ion do I get? What ion do I get when I put it into solution? There's only there's 2 important ions we've been working all of our pH formulas with. Right, it has a hydroxide in it, so it would of course deliver it. There's no tricks right here. It's literally right there. So when this SrOH2 goes into solution, this is one of the special cases. There's only 3 bases that do this. What ratio of hydroxides does it make to itself? It doubles because of that 2 back here. So for every strontium hydroxide, it's going to make a strontium 2 plus and 2 hydroxides. So this concentration is not the concentration of hydroxide. What do I need to do to that? Double it. So that's what? 0.2494 molar. That would be the concentration of hydroxide that you must use to get to pH. Well, can you jump from OH to pH? No. What do you plug it into? Right, so we're going to plug that into the POH formula. So can you guys calculate for me? My little human calculators. This goes into POH equals negative log of OH concentration. So it's negative log of 0.2494. Buddy? I'm good with that. Okay, so that's POH, right? Alright, so then if that's POH, how do I get to pH? Right, so pH plus POH is equal to 14. So 14 minus POH is 14 minus 0.6031. So that's 13.3. Thank you. 69. And that's basic, right? And that should be, because this is a strong base, so it should be pretty basic. All right, so take some time, finish up the rest of those last three on the back, on the right hand side of that page. I guess you're good. I really want you to get down to 3 on that one because they start you off with some different data, right? Start you off with like 55 milligrams or something.
Yeah.
So that if you want to start from the bottom and work up, that's fine. That one's pretty important too.